How are we gonna pick our ornament up?
Only if we had fluid mechanics.
This ball is floating inside of a funnel with no strings, no magnets, just air. We'll be using fluid mechanics to show that this is possible, and yes, we are blowing air.
Our challenge was to create a device that could pick up a lightweight object while only blowing air. The problem with that was, how do you create enough lift or enough stability or even allow it to stay in that area when it's low pressure?
When air is forced through a narrow opening, it speeds up. According to Bernoulli's principle, faster air has lower pressure.
The reason the ball stays centered in the funnel is the Coanda effect. When fast air flows along a curved surface like the ball, it tends to stay attached instead of moving straight. If the ball shifts to one side, the airflow sticks harder to that side, lowering the pressure and pulling the ball back to the center. This creates a low pressure region along the sides of the ball and the bottom. This behavior comes directly from the Navier-Stokes equations, which describe how viscosity and momentum in a real fluid cause the flow to curve and create these restoring forces.
So all we used was an air mattress pump, tubing, and a 0.6 inch throat funnel, which actually accelerates the air, and we found the flow rate of that with this video.
To the airflow of our pump, we used a 60-gallon trash bag. We sealed the tubing into the bag, timed how long it took to fully inflate, and divided the bag's volume by the fill time.
All right, and here we have that same funnel, and then we have a 60 millimeter hollow plastic ball that weighs about 7 grams. The reason we use this one was that it actually fits this one a bit better. Flow can go around it easier compared to one of the smaller funnels that we have and have experimented with.
We were initially going to use a ping pong ball, but then we found out that the nozzle diameter size matters a lot in relation to the diameter of the ball, because when we tried using the ping pong with this larger funnel, we ran into some issues where it would be pushing the ball out, and we think that the Coanda effect can't properly happen when there's a much larger area, and it won't go around the ball to create that pressure difference.
Here we're using SOLIDWORKS flow simulation to actually visualize what's inside the funnel. In this pressure plot, we can see that the blue region is a lower pressure than that of the bottom region. That pressure difference is what causes the upward force that beats gravity. In this velocity plot, we actually see that it speeds up where that low pressure zone was. So fast air means low pressure, just like Bernoulli predicts. And the high speed jet around the fast ball is what's keeping it levitated and stable inside the funnel.
Using our earlier flow rate calculation, we can find the velocity of the air from the pump. Using Bernoulli's equation to show the difference in pressure acting on the ball as a force, this ends up being 3.22 newtons of lift, which is greater than the 0.0686 Newton weight of the ball.
Another thing we noticed is that the ball starts spinning. That happens because nothing is perfectly smooth or perfectly centered. Even tiny bumps or slight differences in the gap will make one side of the ball get faster airflow. That uneven drag creates a torque that starts the spin, and once it's rotating, the Magnus effect will keep it stable. And with all that information, we should be able to pick up all the ornaments before the holidays.
Yay!